Alright, time for another draftphysics.com. Debatephysics.com also, but debate is hard to find, especially at places like Shittopedia, where if you challenge the authorities, the editors, in any way, you're not going to last long, and they're just going to block you for life for doing nothing but disagreeing with them and providing evidence supporting your disagreement. They just won't hear it. It's just not allowed. So anyway, gravity. And I'm not going to bother reading from a Wikipedia page this time, just pointing out all the experiments, or some of the many experiments, that they've never bothered to do. They've never bothered to inquire. What's the answer? None of that. So this one's a rather simple one. You take a spring and you're going to weigh something. So you can put an elephant on the spring, or you can put a mouse on the spring, and then you just lock it in a position. So whatever it moves, you just lock that position and then turn it horizontally and see what kind of motion, okay, in some sort of frictionless environment, you're able to produce. And the argument is that what you're going to end up with is 1 mile per hour. So whether I put an elephant on or I put a mouse on, when I turn it, I'll push that mass 1 mile per hour. So 1 mile per hour is how fast you're essentially going into the Earth. And it really is about a question that, like I said, they never talk about. They don't bring it up. They don't have anything to say on the subject. But the fact is, you're moving into the Earth, and the Earth does have to push you back up to where you started. So in a sense, you might be able to understand that when you're moving this way, when you're being accelerated in this direction, okay, you're using a force, okay, that had to push you, and that force has now been slowed down because you're going pretty slow into the Earth. And so you've degraded the force that was going the speed of light, and now it's not going the speed of light as it pushes you down, and therefore it's not getting to this other side of the Earth. So the other people on the other side of the Earth aren't going to feel a force because you consumed it going down. And then the same thing happens when the Earth pushes you back up. It's using energy to push you back up, okay? It's consuming it again, and therefore out here now feels less force because you're consuming force to move this way. So every time a piece of matter, an electron or a proton, every time it moves, it has to only move in one direction. It can't go both ways. So it literally does go this way, and then it goes back this way, and then it goes back this way, and then it goes back this way. So every time, this side only sees the consumption of force in this direction. If I'm sitting here and you use up a force to go this way, I can't feel that. I can't know that happened. But I'm certainly going to know when you're going this way that you used the force. So I'm only going to get half the force that I would have gotten if you're going back and forth. There's only half the force it's going to get here. This is all discussions physics won't have, they don't think about. They don't think about the actual nature of motion on the elemental scale. And the idea is that something moves, and it can't move for free. Something has to be used to move it. There's no free motion. So this can't move unless something else essentially stops moving. So if it's a big thing, they can understand it because you see this thing crashes into this thing leaves with motion, this one stops. So you can literally see the idea that for something to move, something else has to stop. And the fact is, on the elemental universe, that's sort of happening in the sense that electrons and protons can't move unless they use something else's motion. And the motion is in the form of the little photon-like crap that's in the universe, and it hits it, and while it's moving the matter, it'll go a lot slower than it would have gone if it wasn't pushing a big giant clump of matter. So it loses a little of its velocity to give the matter velocity. And Yeah, and so that's the deficit that creates gravity. All right, now we'll go to another experiment never contemplated by physics. Try a different pen, actually. All right, so as a thought experiment, because we don't have the real experiment, there are experiments that would resolve an issue once and for all. Is gravity about time, or is it about distance? So yes, conventional physics says it's about distance. It's about how far something falls in gravity, and you somehow get your units of energy based on how many units of distance you fall. Now, the simple experiment that could prove it one way or the other is to basically drop something in a staircase kind of manner. So, let it fall, and then let it fall, and then let it fall, and then let it fall. So you could have 4 units of distance, all right, but you would have twice the amount of time. To do this, it would take, let's say it takes 1 second to fall 1 unit of distance in this case. So this would be 1, this would be 2 seconds, 3 seconds, 4 seconds. It would take 4 seconds for it to fall this way, and only 2 seconds to fall this way, because it goes this distance in 1 second and then this distance in the second second. All right, so will these two things create the same energy? So if you were trying to it's coming up with a good way to demonstrate how much energy something has without involving something that can't store the energy as impulse. And so a spring won't work because a spring already has tension in it. You can't hit it 4 times with the same weak energy and push the spring further. The spring won't go any further because you won't be applying any more energy than it already has stored in it. And the same would be true if you used a fluid that went up in gravity. Say if you push down here and you move fluid up on some other side, that fluid would have gravitation pushing it down, and that pressure would have to get overcome, so it would sort of destroy the experiment in this sense. This won't work. So the only way you can really do it is like push something into a substance. Let's say you had a blob of clay here and you pushed a nail into it. That way that each hit would have its own independent force that it would be applying, and you could just measure how far the nail goes in. Now the simple argument is this will only have 2 units of energy because it was only in the gravity 2 units of time. It's 9.8 meters per 1 second. One second. All right, and over here, you're going to get 4 units because you're going to have 4 units of time, and so this will go 4 times deeper. So this would have 4x, 4 units of energy. It's not 4x, 4 energies. So it'll go in. It will penetrate 4 times. This will only penetrate 2 times, let's just say. So this will be twice the penetration because it is twice the time, and it will be twice the energy. And the simple fact will be revealed that these are the same distances. This total distance, okay, will be the same as this total distance. So the distances will be identical, but the outcome won't be. Demonstrating that it isn't about how far something falls. It's about how it falls, and more specifically, the how tells you how much time it falls, and it's how much time it's actually falling is the only part that matters. Obviously, this will take longer than 4 seconds because you got to have this little bit of time to go this way, But we're just talking about the actual falling time will be 4 seconds, and this would be 2 seconds. So it's a good experiment if somebody can do it. To basically prove that it's not, about the distance. Force times distance is not energy. Okay, that's what they're basically saying. It's force times time. How long the force is applied will decide how much work or energy you're going to get out of it. Alright, so as a counter argument to what some people might argue is a failure of some kind of particle theory to accurately describe the circumstance, somebody might argue that if you had a shaped object in gravity, that this object would somehow be more affected by gravity than this object. And this relates to something observed by Newton. One of his arguments for not being an ether is that when force goes in, something is gravitationally pushed, it is a straight down force. And then when stuff is released, like you create heat or you create steam, the steam moves in all directions. Okay, it doesn't have a preference, and it's only through more complex actions of convection that there can be any preference in motion. It's basically stuff can go in all directions. So gravity goes straight in, forces opposed go in non-straight directions. So anyway, the point would be is that the theory isn't that there's a bunch of force going straight down. The point is that there's force coming at all angles. And so you're being hit by gravity sideways. It's just that sideways, okay, cancels. Every motion this way gets canceled by the motion that way. So any vectors, like they're going in, say, this direction and this direction, you can understand that there's two components to that. One component going this way and a component going down this way. And these two components are opposed to each other, and these two add. So this adds to this, while this action goes this way and this action goes back the other way, and you end up with nothing. And so there's no obvious motion created by these two opposing forces. So the part that's opposing this way and opposing this way can't create any observable motion. It can just create jitter, where the motion, the component in the downward direction, does add, because it's both in the same direction. So they contribute to each other and cause the object to actually move. So the object won't move this way and this way observably, because the two actions undo each other. But you'll see it go this way, because all of these arrows have a component down, down, down. So they're all adding that component down, and that's creating the force. And so, yes, if you have the surface this way, you collect lots of energy in all these directions, but the same is true here. If I create a longer object, then there's all this energy here, all the stuff this one's missing. This one is only collecting a little tiny bit here, and it's collecting a lot across this surface. Well, this one's going to do the opposite. It's going to collect very little coming down this way, but it's going to collect a lot going down this way. So all of the stuff coming from this angle, any one of these angles, all of that energy gets converted into this, because all the sideways energy cancels. So you get a big arrow of down, because you're going through it at a lot of these angles. So you can't really change how much motion the object gets by turning it in the gravity, because no matter which way you turn it, you expose it to a whole different set of, you could call them photons. You can't change how many hit you by changing the angle, because unlike most light sources that have directionality, gravity's light coming from all directions. So it doesn't matter which way I turn something, because the light's coming in all directions, except from the bottom, of course. I mean, obviously things are being hit from this direction, and the Earth is the one that's got the big minus, So you really have to just think of it being in a world where this side's going up and this side's going down, this side's going up and this side's pushing down, and you're just looking for any place where there's less doing this, okay, than there is stuff doing this. And that's what the motion is creating. The motion of the stuff inside of the Earth has consumed some of the energy, so there is in fact less going this way than there is coming down this way, and there's more going this way than there is coming out of the Earth this way. And most dramatically, obviously, the longer the travel through the Earth, the more likely the force has been delayed. So obviously the strongest amount of differential would be straight up and down, but all of these still count. So all of these other directions, all right, still create the total effect of the gravity. So you can't create more gravity by having something in different positions, because the gravity, the force you're collecting, is coming from all kinds of angles. So even something with a very, like even gravity coming almost horizontally, you know, just a little tiny 1% angle, that 1% angle still has a piece of energy going down. Yeah, most of its energy is going this way, but it still has a little piece going down, and the object will collect that little piece. Alright, another slightly more complicated argument. I don't know if complicated is the right word, but let's say there was a place in the universe where there was exactly the same amount of energy moving in these two directions over time. So over the totality of time, it's, you know, 1 trillion little things hit from this way and 1 trillion move this way. And then you have a piece of matter in there. And let's say that that balance is destroyed because at one moment you add one more, just one. So it's 1 trillion and one over here and 1 trillion over here. What's the consequence? And this just keeps going on, you know, on and on and on and on. It's always equal except for that one little extra bit that you threw in from this side. The argument would be is that yes, this side, this one gets it, hits and moves it in this direction. And what happens is now it's moving into this force. And that means that it's more likely to get hit this way than this way. And so it's going to end up having its motion stopped. Okay. And then probably going to be pushed back a little. And then that means that while it was going this way, it moved ahead of all of this force. Okay, it's a little bit ahead of it. So it wasn't getting hit by as much. If it goes in the opposite direction or it stops, it's obviously going to be hit by more because there's stuff going to catch up to it. It went a little bit faster than the force, so it didn't get hit by as much force. And so now that extra force that was almost hitting it, but couldn't quite hit it because it was moving a little bit, that is going to be more force, and therefore it's going to go this way, you know, and then it's going to stop, and then it's going to go this way, and then it's going to stop, and then it's going to go this way, and then it's going to stop, and it's going to go this way. So it's the energy is essentially forever. So once you put more in a direction, and you don't actually put another extra bit in from over here, inevitably this thing will move that way forever. It'll just keep going. That one little thing will push this forever. Now it's going to push it kind of slowly because it's stopping and starting and stopping and starting and stopping and starting. So it's going to do it in a, you know, a herky-jerky kind of manner. But through time, it's always going to go a little bit more this way than that way because of that one little extra bit. So it's just a way of understanding that it's, you know, it's not as simple as just saying you hit something and, you know, it goes, because it's going into a field of energy, and that energy is going to react, and then there'll be a reaction and another reaction, and that play is going to continue. So you really can't get rid of any imbalance created in a direction, and inevitably it's like, you know, in the end, the thermodynamics of the universe ends up evening out, because wherever you do have this deficit, something will fill the deficit. You know, if I took this piece of energy from some other place, you know, say there's another place in space, and I took this piece of energy, this extra that was in this area, from some other place, well then I would have created some deficit in the opposite direction. Somewhere in the universe there's a place where there's missing one of these arrows and there's an extra one of those. So no matter what, if you have motion going this way somewhere in the universe, there is motion somewhere else going that way. So you can understand that on balance, all of the motion in the universe, you know, galaxies spinning, things moving in all kinds of ways, that there's essentially a counterpart to every one of those motions. So anything moving has a counterpart where the deficit was created, and something else is moving in the opposite direction, essentially filling that deficit. So so the total spin of the universe would be nothing, because all the spins have to have a counterpart. Every arrow I put, every extra energy I put in one piece of space, I had to take it from some other piece of space. And I created an imbalance somewhere else. So again, not really a subject physics deals with at all. Don't even talk about it. Alright, let's do a little bit about the rate of force and understanding what the gravitational constant is, and of the value of the simple statement of 9.8 meters per second per 1 second. Alright, so it's 9.8 meters of velocity that's added per every 1 second. So there is no seconds squared. There's a ratio. And if you change this number to a 2 or some other number, then you have to change this number, because the ratio has to always be 9.8 to 1, or 19.6 to 2, or 4.9 to 0.5. I mean, it has to be the same ratio. You can't change this fraction, or you're making a mess. So the gravitational constant, from how I look at it, should be understood as there is, okay, an amount of stuff coming out of something. So you could say it was a sun or whatever it was. And it's just easier to do it as a going out than an in thing. And all that you're saying is there's a certain number of bits. All right, so they're being ejected. So if the gravitational constant was some number, 6.72 times something else, it doesn't matter. It's just really just saying that there's a certain number of these things being emitted. And the fact is, you can use this r squared term to figure out your distance from that point where all of this stuff is being ejected, this 6.9 thing. So let's just say it's 6 million. So there's 6 million things being ejected, obviously every unit of time. So this would be, the gravitational constant would essentially be in units of time. That's the only way you can measure this volume. You can't just say a volume, you have to say a volume in an amount of time. And so all of this stuff is being ejected, and the r squared thing is really just telling you, okay, because it's moving in 2 dimensions, it's spreading in 2 dimensions, it's spreading this way and it's spreading this way, that it's getting less dense with distance by those 2 factors. This one's cutting it in half and this one's cutting it in half, and those 2 halves multiply to create a square, a volume of diminishment. Okay, the square is here, okay, in the sense of you're spreading in 2 dimensions, and so it's all right. So anyway, so you know there's that many coming out. So you know right here, you know, if you put a thing here that, well, you don't need, no, just put one object. So if we just put any one object, so yeah, we'll just make this a bigger circle. Okay, so if you put an object here, you know it's going to be hit by more of this stuff because it's going to be denser per inch here, okay, close, than it's going to be far away. And that's the r squared thing. You're just telling you how much density there's going to be. So this is the amount that's being produced, and this r is telling you how much you've diminished it by going a distance from the center. And obviously that doesn't account for inside the object, but we're just saying that it's for analysis purposes. You're just thinking of this as a point in space that's doing all this ejecting. So anyway, so all it's really saying is, yeah, the further away you are by the r squared factor, that means it's twice the distance is 4 times less. Okay, so you go a unit of distance, and it's 4 times less, not 2 times less. So you just keep saying 4 times less instead of 2 times less. And so that's all that's really in the equation. There's no room for a squared factor or any of that kind of stuff. You're just saying there's a certain density of stuff. That's the constant. And the r squared is just telling you how far you are from the density, how much you've diluted the density. So the further you go away you go. See, I mean, the way to really draw this is the kind of Gaussian way, where you just put a bunch of lines in here, so many lines. And you just say, if I put the object here, it crosses 3 lines. If I put the object out here, it only crosses 1 line. So you can see if you put a whole bunch of lines, you could just count how many lines it breaks, and that'll tell you how much of the force it's affected by. So when it says 9.8 for us, it's really just establishing how much the force is diluted at the position we are from the absolute maximum. So basically it's just saying how many of the 6 trillion are we going to get hit by at any one position, and it's based on our mass. Is basically saying how big are you. The mass is the collector. It's like a sail. It's just saying how much of that force can hit you. So that's your mass. It's just saying what's the hittable area of your substance. How much of you can collect the force, and that's your mass. And so the mass just tells you how much you can collect, and the distance tells you how much it's been diluted at the distance you're collecting it, and then you end up with this number. So at different distances the number changes, and it's going to be in per second units, because it's talking about a constant amount of radiation that's coming out at a constant amount per a unit of time. The gravitational constant is producing energy in units of time, not as totals, not as nets, but as individual moments of time in the universe. It's producing an amount of force, and you're collecting it based on how far you are from that source. But there's no squared seconds, so they write 9.8. You know, physics says that, you know, they write the 9.8, and then they say meters, and then / seconds squared. There's no seconds squared. It's a ratio, 9.8 to 1. That's the ratio, 1 unit of time. The same unit that the force itself, the constant, is. And you're just saying this is the percentage of the constant. Okay. Not perfect, but good enough. Alright, so I think we'll call this a video. And just to sort of summarize on gravity, and you know, we'll do some other subjects and such. So, till the next time. This has been draftphysics.com and debatephysics.com video presentation and such.